We are going to dive into mathematical statistics and derive the rth moment for a specific continuous probability distribution known as the beta distribution of the second kind, or the Pearson Type VI distribution. By the end of this video, you will be able to set up the integral for the rth moment and use the properties of the gamma function to arrive at a clean, algebraic expression for the result. Let's start with the probability density function, or PDF, provided here. This function describes how the probability is distributed for values of x greater than 0. Our goal is to find the expected value of x raised to the power of r. We want to show that the rth moment equals the product of alpha plus r minus 1, alpha plus r minus 2, down to alpha, all divided by the product of beta minus 1, beta minus 2, down to beta minus r. To find the rth moment, we need to calculate the expectation of x to the power of r. By definition, for a continuous random variable, this is the integral over all possible values of x, in this case, from 0 to infinity, of x to the power of r multiplied by the probability density function. Let's substitute our specific PDF into this formula. Notice that the term involving gamma functions is a constant with respect to x, so we can pull it outside the integral. Also, notice that we have two powers of x to the r, and x to the alpha minus 1. When we multiply these, we add the exponents to get x to the power of alpha plus r minus 1. This integral looks very similar to the definition of the beta function. In the next step, we will identify the parameters needed to evaluate this integral directly. To evaluate our integral, we need to recognize a specific form of the beta function. There is a known identity that relates the beta function to an improper integral. Notice the structure. We have a variable to a power in the numerator, and 1 plus that variable to a different power in the denominator. Let's compare this to our current integral. To match the exponents, we can set our first parameter m equal to alpha plus r. Now, look at the denominator power. In the formula, the exponent is m plus n. In our integral, the exponent is alpha plus beta. By solving for n, we find that n must be beta minus r. This allows us to replace the entire integral with a single beta function. So, the integral part of our moment calculation is simply the beta function evaluated at alpha plus r and beta minus r. Now, let's combine everything we've found back into our equation for the rth moment. We have our leading constant and the result from our integral. To simplify this further, we use the identity that relates the beta function to the gamma function. Let's apply this identity to the beta term on the right. Notice what happens in the denominator of the second fraction. The positive r and negative r cancel out, leaving us with just gamma of alpha plus beta. We can now see that the term gamma of alpha plus beta appears in both the numerator and the denominator. After canceling those terms, we are left with a much simpler expression for the moment. This is the general form of the rth moment using gamma functions. In the next scene, we will expand these gamma functions to reach the algebraic form we were asked to prove. To reach our final goal, we need to use a fundamental property of the gamma function. Recall that gamma of n plus 1 equals n times gamma of n. We can apply this repeatedly to expand the terms in our expression. Let's start with gamma of alpha plus r. By applying the property, we can pull out alpha plus r minus 1, then alpha plus r minus 2, and so on, until we reach gamma of alpha. We can do something similar for gamma of beta in the denominator. Since we want to cancel out the gamma of beta minus r in the numerator, we expand gamma of beta down until we hit that term. This gives us the product of beta minus 1, beta minus 2, all the way down to beta minus r, times gamma of beta minus r. Now, let's look at what cancels out. The gamma of alpha on top cancels with the 1 on the bottom. The gamma of beta minus r on top cancels with the 1 on the bottom. What we are left with is exactly the expression we set out to prove. We have successfully derived the rth moment by leveraging the relationship between the beta and gamma functions. This formula is extremely useful for finding the mean and variance of this distribution by simply plugging in r equals 1 or r equals 2. Great job following along.